The next type of differential equation, first order, that we're going to look at is something called a Bernoulli equation. A Bernoulli equation is very similar to a linear equation in the form, except for one difference. Okay, so you may remember that a linear differential equation has the form y prime plus p of xy equals q of x. And this differential that we're looking at has almost the same form, but we have this y to the nth power. And that means that we're not only looking at a first order differential, but we're also looking at this nonlinear type of differential. All right, so it's the only nonlinear differential that we're going to look at of the first order that has an exact solution to it. All right, so we are not looking at a linear differential, we're looking at a Bernoulli equation. And so to be able to solve this, what we're going to do is we're going to be able to use a substitution. And the substitution we're going to make for this is that v is equal to y to the 1 minus n, where n is the exponent of the nonlinear factor that's affixed to q of x. Right? So it's very similar to the other substitution problems that we looked at before. We have to solve and we have to substitute not only for y, but also for y prime. We're going to get it, instead of in terms of x and y, we're going to get it in terms of v and x, and then we're going to solve and back substitute. So it's very similar to what we had before, except this is just a different substitution. So let's take a look at an example, a basic example of one of these types. So we have y prime equals y plus e to the xy squared. Notice immediately we have y squared. That means we have a nonlinear differential equation. And the only nonlinear differential of the first order that we're going to look at, aside from at the end of the course, is going to be a Bernoulli equation. All right, so that's what your clue is to know when to use a Bernoulli equation, is that it's almost linear except it has one of these nonlinear terms. So what we're going to do is we're going to identify this as a Bernoulli equation with n is equal to 2, as evidenced by y squared, and we're going to say that the substitution we use is v is equal to y to the 1 minus 2, or y to the minus 1. If we solve that for y, that means v to the minus 1 is equal to y, just by raising both sides to the minus 1 power. And then finally we can find the derivative of both sides, because we need to substitute for not just y, but y prime. So y prime is going to be equal to negative v to the minus 2 dv dx. So let's do this substitution and let's see what happens. All right, so we already know, and the other thing we probably want to do is want to put it into the form of one of these Bernoulli equations, which means we're going to have to move the y in the original equation to the left-hand side. So y prime minus y equals e to the xy squared. And then by substitution, remember y prime is going to be minus v to the minus 2 dv dx minus y, and remember we said that y was equal to v to the minus 1, and that's going to be equal to e to the x times y, so that was, remember, v to the minus 1 squared. Or, in other words, if we simplify that just a little bit by using some basic algebra, minus v to the minus 2 dv dx minus v to the minus 1 is equal to e to the x v to the minus 2. All right, so remember, when you raise a power to a power, you multiply those. Now what we have this time is we have a linear differential. And how do we know it's linear? Well, let's start by dividing everything by minus v to the minus 2. All right, so when we divide out, we get dv dx plus v. All right, so notice that this negative and negative becomes a positive. Negative 1 minus a minus 2 is just v to the first, is equal to these v to the minus 2's cancel out, and we get minus e to the x. All right, and it's a perfect linear differential equation. Right? So now what we remember is that we need an integration factor. Now remember, the integration factor I is going to be equal to e to the integral of p of x dx. All right, so just reminding us. Remember, p of x is going to be the coefficient of whatever's in front of the term y, or in this case v. So in this case, p of x is equal to 1. So that's going to be e to the integral of 1 dx, or in other words, e to the x. And now we're going to shove it right back into our equation. All right, so remember, our equation, not for y, but for v this time, is going to be 1 over the integration factor, integral of q of x times the integration factor dx plus c. All right, so remember, that's our formula that we'd found from before. Or in other words, remember we found that I was e to the x. Remember we said that q of x in this case is going to be what's on the right-hand side, which in this case is negative e to the x. And notice what this is going to work out really well. So it's going to be 1 over I, which is e to the x, integral of q of x, which is negative e to the x, times I, which is e to the x, dx plus c. And notice this is getting really nice. We can simplify the algebra inside of there. So that's going to be the integral of negative e to the 2x, not x squared, but 2x dx plus c. Right, remember, it's x squared if you're going to raise the x to a power or something of that nature. But remember, when they're like bases, you just add the exponents. We're going to be left with 1 over e to the x. Remember, if we're going to do the reverse of the chain rule, all right, so we have this negative e to the 2x. If it was a derivative, it would be negative 2e to the 2x, but because it's an antiderivative, we're going to have negative 1/2 e to the 2x. And then we still have our plus c. We can distribute the e to the x, so that's going to be minus 1/2 e to the x, all right, plus c over e to the x. And remember, that's v. So the very last thing that we need to do is we need to back substitute for v, and then if at all possible, we need to solve. All right, so remember, v was equal to y to the minus 1. All right, and how do we know that? We go all the way back up here. Remember, v equal y to the minus 1. So now we get y to the minus 1 equals minus 1/2 e to the x plus c over e to the x. And then finally, we just raise both sides to the minus 1 power. So this is one possible solution. All right, might not be the nicest one, but it is a solution. All right. I don't remember if this was an initial value. Let me go back up. Nope, it's just solve. All right, so we just need the general solution for this, and this is our general solution. All right, so hopefully that gives you a good overview as to the process of being able to solve a Bernoulli equation. Now in the next videos, we're just going to do a couple more rigorous examples of how to solve one of these types of Bernoulli equations.